the end of this short video, I hope that you're able to identify the differences between systematic and random errors or uncertainties. First of all, let's discuss what uncertainties or errors actually are. A common misconception is that errors or uncertainties are caused by mistakes made by the experimenter. This isn't true. Mistakes made by the experimenter can lead to errors or uncertainties, but they're not the only source of errors and uncertainties. Errors and uncertainties can come about due to a number of reasons. The method that an experimenter chooses to use can have inherent uncertainties in it. There's also limitations in the precision of the equipment, such as the markings on this meter ruler limit the precision and accuracy to which I can take measurements with this ruler. We've also got calibration errors that occur within the equipment, either because it's not zeroed properly or just because of the nature of the equipment. And there can also be experimental noise and random fluctuations in the values that we're actually measuring. So we can divide uncertainties into two big categories. We've got systematic errors. Systematic errors are errors that have a non-zero mean. So this means that the errors tend to be positive or negative. So these errors cause us to consistently overestimate or underestimate the actual value that we're using. So typical sources of systematic errors include calibration errors. So one type of calibration error is a zero error. For example, if you're using a set of digital scales at home, and before you put anything onto the scales, it says 5 grams. Then whatever mass you measure is going to be overestimated by 5 grams. So this is a systematic error. Zero errors aren't the only type of calibration errors. Some equipment can overestimate a value by, say, 5% every time, which is also a calibration error. Other types of systematic errors can come about due to limitations of the technique. So, for example, if you're measuring the speed of sound using a tube, you need to take into account the end effects of the tube because the antinode is actually found a little bit outside the tube rather than at the end of the tube. And if you don't take that into account, then you're going to have a systematic error in your results. The other broad type of uncertainties are random uncertainties. Random uncertainties are uncertainties with a zero mean. This means that we're just as likely to overestimate the value as underestimate it. Some common sources of random uncertainties include experimental noise and also the precision of the equipment. So, for example, this meter ruler is marked in increments of 1 millimeter. Each of these little markings is 1 millimeter from the next one. So we can measure things with this ruler down to a precision of half that smallest increment. So because the markings are 1 millimeter apart, we can measure things down to a precision of 0.5 millimeters. So for example, if I were to measure this pen by aligning it perfectly with the end of the ruler tells me that this pen is 14.1 centimeters long. Now, in order to write down the length of the pen, I should write it as 14.10 plus or minus 0.05 centimeters long in order to account for the limitations of the precision of this meter ruler. Random errors can also come about due to random fluctuations in the values that we're measuring. So for example, if you were measuring the background radiation, this varies, and so you've got random noise or random uncertainties associated with that. So random uncertainties have a zero mean. So in conclusion, we've got two main types of uncertainties, and these uncertainties need to be dealt with differently. We've got systematic errors which have a non-zero mean, and random errors that have a zero mean. In later videos, we'll be looking at how to deal with each of these types of uncertainties.